Now you can kind of sense in all those examples, the difference is how big is the B. If B equals 0, that's the harmonic solution. That's B equals 0. Nothing, no energy lost. And that's B equals 6. And that's B equals 10. So over-damping, under-damping, critical damping, it's all depends on how big, how small is your B. Now, when the delta is less than 0, B squared less than 4mk, B less than 2 square root of mk, then you got over-damping, under-damping. Then you have a trig solution. Not only trig, of course, you have exponential too. When the delta is positive, that means B bigger than 2mk, you got the over-damping. That's like example 6. And the last one, when the delta equals 0, B equal exactly mk, you get the critical damping. So that's all. By definition, under-damping, over-damping, and critical damping. Well, now you figured it out from mathematics point of view. Can you connect this to the physical science point of view? The B, if you remember, is the friction. It's the relative strength between the resistance and restoration force. So if the resistance are too big, like the overdamping, your spring is relatively too weak to pull the mass back to the other side. That's overdamping. And if the spring is strong enough, can pull it back and let it bounce back and forth, that's overdamping. And the critical damping is just the board between overdamp and underdamp. If a little bit small, B make it underdamped, a little bit big B make it overdamping. So now that's the connection between physical science and the mathematics equation. We already talked about this. And I want you to calculate one more time and look what we did here. The B and mk, that's the mk. And the first one, example 3, underdamping, because B less than 100. 6 squared, that's negative. And the 5, overdamping, well, you can just check. And the number 4, critical damping. Well, I'm going to spend just a few minutes show you how to solve it by using the shortcut. Well, that's why in other class we need to take weeks. I'm not going to spend that time. I'm going to let you either use MATLAB, Maple, Mathematica, they all can solve this. And the keyword is solve. I skipped a few pages. How do you look at the complex root? And all you need is remember the Euler formula, nothing else. And now skip to the Maple command. First, let me give you 3 examples. Again, let me change this. That's 26, that's 6. Have 3 different B, damping effector, And the one is 26, big. Second one is 10. In the middle, the last one is 6, small. The K, again, 25. And then this time, I don't do by hands. I use the maple command, define the 3 equations. They're all the same. You can copy paste, by the way. That's how I do it. The difference is right here. And then the second command you call is dsolve. Put your differential equation here. D means differential, by the way. If you use the solve, that's solve algebraic equation. And dsolve means solve a differential equation. So when you put the dsolve, they're going to give you the solution. Let's look at what the solution looks like. The solution one, it's over damp problem, and I want to check delta. You remember the b equal 26. It's 26 squared minus 4 times 25 equals 24 squared, positive. That's over damper. And then you get the 2 exponential function. And the second one, the b equal 10, the delta equals 10 squared minus 4 times 25, which equals 0. You got the so-called critical damping. The critical damping have one root r equal -5. The second solution is just multiply the x to the same solution. That's when you have this critical damping. The third one, we have done it, showed you how to check it, and we did it. It's a trigonometric function e to the 4x. And that's the predominant case. It's attenuating oscillation. And that's exact answer for the example 2 and 3. Okay. Well, next, how do you solve an initial value problem when you add these two initial conditions? Well, typically, if I teach differential equation, I give a question like that, I give a student 20 minutes to do it. They usually can do that. But here, you only need 2 seconds. You define the initial condition in this way. And we already defined the ODE in the previous slides. You see, the third ODE is here, we defined. And then, all you need is call this command, dsolve, put the brace here. That's the ODE. This is the initial condition. And you click the mouse, you get this solution, which is what I gave in example 3, if you remember. The only thing is I use t, this time I use x. Doesn't matter. You can write this as x t equal e to the -3t sine 4t plus cosine 4t. It's just a different convention. T is time. Well, the last one, pretty complicated one. All the previous examples I showed you are homogeneous. This one, when I add the external force, it's inhomogeneous equation. Well, the maple can do the same way. And you have an initial condition. I just defined the fourth equation. And the right hand, you remember we get this, and the plus 4. And bring the initial condition here. Use the dsolve. What you find is this is the homogeneous solution. And this is the particular solution to the right hand. And we find that the complete solution very quickly. So for the exercise, I only ask you to do the simple, easy thing by using the hand solution. and characteristic equation. And the complex roots for the trigonometry function or inhomogeneous, you're just welcome to use Maple, MATLAB, Mathematica. By the way, Mathematica have no much difference. It's also dissolve the same command. If you use Mathematica, all you need is change the parentheses into brackets. I think that's the only difference I observed. Well, let me summarize what's important. So we start from a physical science phenomenon. Depends on the relative strength of the spring restoration force and the resistance damping force. So the behavior of the system could be underdamped and attenuating oscillation, overdamped, no oscillation at all, critical damped, no oscillation, it's just decaying, or a harmonic function, which is unrealistic, when there's no resistance at all. So there's three phenomena. It really depends in the mathematics, the three phenomena of the quadratic equation. When the discriminant is negative, positive, or 0. So that's the match. That's negative, positive, and 0. That's the most important knowledge for today. And the characteristic equation, you simply change the differential equation for the order of a derivative to the degree of the algebraic equation, and that equation we call it a characteristic equation of this homogeneous ODE. And another element is, what about the R equals like negative 3 plus 4i, R equal negative 3 minus 4i? By the way, they usually come in pair as a conjugate. And then your solution will be e to the negative 3 cosine 4t and sine 4t. Put a C1, C2. That's your solution. And finally, to do the homework, you don't just click the mouse and go. You need to connect the knowledge you learned today, the discriminant, the characteristic equation, and the phenomenon. If you can do this, you are good to move on. I'm going to spend another hour. In a couple of hours later, use the system differential equation to solve it. I'm going to use a stellar instead of a maple and simulate the behavior. But it's good to have the basic knowledge before we move on to the system equations. I'll see you next time. Thank you.